In molecular orbital MO theory, each electron belongs to a molecular orbital that spreads over the whole molecule. The simplest way to build these orbitals is the linear combination of atomic orbitals LCAO method. Think of two singers singing the same note. When they sing in phase, their sound waves line up, the volume becomes louder. This is analogous to a constructive combination that forms a bonding MO. When they sing out of phase, one wave is upside down. The sound cancels, like a destructive combination that creates an antibonding MO. Mathematically, we write psi bond equals C1 phi A plus C2 phi B. Psi anti equals C1 phi A minus C2 phi B, where phi A and phi B are the atomic orbitals of OS on atoms A and B, and C1, C2 are coefficients that reflect how much each O contributes. The coefficients are obtained by solving the secular determinant, which contains the overlap integral S equals the overlap integral of phi A and phi B. Larger overlap good spatial match makes C1 and C2 nearly equal, giving a strong bond. Symmetry is also crucial. Only a OS of the same symmetry, for example both S or both PZ, can combine. For homonuclear diatomics, the combined orbitals are labeled gerade, G, symmetric with respect to inversion, or ungerade, U, antisymmetric. A 1s plus 1s combination gives a sigma G bonding orbital, while 1s minus 1s gives a sigma star U antibonding orbital. The energy level diagram for a diatomic molecule shows the relative energies of the molecular orbitals built from the valence atomic orbitals, 2s and 2p for second row elements. For homonuclear diatomics, the ordering follows the rule of symmetry, allowed mixing. For elements up to nitrogen, Z less than or equal to 7, the sigma 2p orbital mixes with the lower energy sigma star 2s because both have sigma G symmetry, pushing sigma 2p up and placing the 2 pi 2p orbitals pi u below it. Sigma 2s less than sigma star 2s less than pi 2p, pi u, less than sigma 2p sigma G less than pi star 2p pi star G less than sigma star 2p sigma star u. For oxygen and fluorine, Z greater than or equal to 8, the energy gap between the 2s and 2p sets widens, diminishing the sp mixing, and the sigma 2p drops below the pi 2p. Sigma 2s less than sigma star 2s less than sigma 2p sigma G less than pi 2p pi u less than pi star 2p pi star G less than sigma star 2p sigma star u. This shift explains why O2 and F2 have a different pattern of filled molecular orbitals compared with N2. The diagram is a ladder where each rung is a molecular orbital labeled by its symmetry, sigma or pi, and whether it is bonding, no star, or antibonding star. Bond order BO quantifies how many electron pair bonds are effectively present. In molecular orbital theory, it is calculated as BO equals the difference between N bonding and N antibonding divided by 2. A higher BO means more electrons are stabilizing the molecule, leading to 3 observable trends. First, bond length. Empirically, bond length D shortens as BO increases because the electron density between the nuclei pulls them closer. The approximate relationship is D proportional to 1 over BO for a given pair of elements. Second, bond strength, dissociation energy D. D grows with BO. A BO of 3, as in nitrogen 2, corresponds to a very strong triple bond about 945 kilojoules per mole, whereas a BO of 0.5, as in fluorine 2, is much weaker. Third, stability. Molecules with BO equal to 0 are not bound, for example helium 2. A positive BO predicts a stable species, while a fractional BO indicates partial bond character, common in radicals. These correlations help chemists anticipate reactivity. A low BO bond is more easily broken in a chemical reaction. Magnetism stems from the spin of electrons. An electron can be thought as a tiny bar magnet. If an MO contains an unpaired electron, the molecule exhibits a net magnetic moment and is paramagnetic. If all electrons are paired, the magnetic moments cancel, giving a diamagnetic substance. MO diagrams make this prediction straightforward. Fill the MOS with electrons following the Pauli exclusion principle and Hund's rule. Any orbital that ends up with a single electron signals paramagnetism. Example O2. Its MO filling using the oxygen-specific ordering ends with two unpaired electrons in the degenerate pi star sub 2p orbitals, giving O2 a magnetic moment of two Bohr magnetons, experimentally observed as paramagnetic. In contrast, N2 has all electrons paired, so it is diamagnetic. This MO-based magnetic prediction matches experimental observations far better than the older valence bond view, which could not explain O2's magnetism. H2. Valence AOS. 1s each H combine to give sigma 1s bonding and sigma star 1s antibonding. Electron count 2 both occupy sigma 1s. BO equals 2 minus 0 divided by 2 equals 1. Bond length approximately 74 picometers, strong single bond. Then 2. Valence AOS. 2s and 2p ordering z less than or equal to 7 gives sigma 2s, sigma star 2s pi 2p twice, sigma 2p pi star 2p, sigma star 2p. Fill sigma 2s squared, sigma star 2s squared, pi 2p to the fourth, sigma 2p squared. Total bonding electrons equals 2 plus 4 plus 2 equals 8, antibonding equals 2. BO equals 8 minus 2 divided by 2 equals 3, triple bond. Bond length approximately 110 picometers, very strong. O2. Ordering z greater than or equal to 8 places sigma 2p before pi 2p. Fill sigma 2s squared, sigma star 2s squared, sigma 2p squared, pi 2p to the fourth, pi star 2p squared. Bonding electrons equals 2 plus 2 plus 4 equals 8. Antibonding electrons equals 2 plus 2 equals 4. BO equals 8 minus 4 divided by 2 equals 2, double bond. 2 unpaired electrons, paramagnetic. Bond length approximately 121 picometers. F2. Same ordering as O2. Fill sigma 2s squared, sigma star 2s squared, sigma 2p squared, pi 2p to the fourth, pi star 2p to the fourth, sigma star 2p squared. Bonding electrons equals 2 plus 2 plus 4 equals 8. Antibonding electrons equals 2 plus 4 plus 2 equals 8. BO equals 8 minus 8 divided by 2 equals 0, technically no net bond. The molecule is weakly bound. Bond dissociation energy approximately 159 kilojoules per mole, and diamagnetic. These numerical examples illustrate how the simple BO formula, combined with MO filling, predicts bond strength, length, and magnetic behavior. When the two atoms are different, the atomic orbital energies are not equal. The molecular orbital coefficients become unequal, reflecting that the electron density is skewed toward the more electronegative atom. The secular equation now contains different Coulomb integrals, alpha A not equal to alpha B, and the overlap integral S may be smaller. CO carbon monoxide. Carbon 2p is higher in energy than oxygen 2p. The resulting sigma and pi bonding molecular orbitals have larger contributions from carbon, while the antibonding molecular orbitals are weighted toward oxygen. The filling gives a bond order of 3 sigma squared pi to the fourth sigma squared, explaining the very strong carbon triple bond oxygen triple bond, approximately 1.13 angstrom. The dipole moment is small and points from carbon negative to oxygen positive, because the electron-rich carbon end partially compensates the electronegativity difference. NO nitric oxide has 11 valence electrons. After filling, we obtain sigma squared pi to the fourth pi star 1, giving a bond order equal to 7 minus 1 divided by 2 equals 3.0. Actually bonding electrons 7, antibonding 1, bond order 3.0. One unpaired electron in pi star makes nitric oxide a radical and paramagnetic. Charge distribution. The extra electron resides mainly on the more electronegative nitrogen, giving a slight negative charge on nitrogen. Cn- cyanide ion is isoelectronic with carbon monoxide but carries an extra electron. Filling yields sigma squared pi to the fourth sigma squared pi star 1, the extra electron occupies the pi star antibonding orbital. Bond order equals 8 minus 2 divided by 2 equals 3, still a strong triple bond, but the extra electron gives the ion a negative charge localized mainly on carbon, the less electronegative atom. These heteronuclear cases illustrate how energy mismatches shift molecular orbital coefficients, affect dipole moments, and modify magnetic properties while the bond order formalism remains valid. The MO idea is not limited to two atom species. For polyatomic molecules, we combine all appropriate atomic orbitals, respecting the molecule's symmetry point group. Group theory tells us which linear combinations, symmetry-adapted linear combinations, SALCs, are allowed. Co2 linear d infinity H. The two oxygen atoms provide pi orbitals that combine to give a symmetric pi g and an antisymmetric pi u SALC. These interact with the central carbon pi to produce two degenerate pi bonding molecular orbitals pi u and two pi star antibonding molecular orbitals pi g star. The sigma framework arises from the carbon 2s and 2pz mixing with oxygen 2s and 2pz, giving sigma g and sigma u. The result is a double bond. Carbon equals oxygen, with bond order equals 2 for each carbon-oxygen link. BF3 trigonal planar di3H. Boron atom uses sp2 hybrids for sigma bonds. The remaining boron 2pz combines with the 3 fluorine pz orbitals to form a delocalized pi system. The 3 fluorine pz SALCs produce one totally symmetric combination, a 1' that strongly overlaps with boron pz bonding pi, and a doubly degenerate E' pair that becomes pi star antibonding. The molecule is planar and exhibits bond order of 1 for each boron-fluorine sigma bond. CH4 tetrahedral Ti-D. The 4 hydrogen 1s orbitals form 4 equivalent SALCs, a 1 plus T2 that hybridize with carbon sp3 orbitals, giving 4 equivalent sigma bonds. No pi molecular orbitals are present. The bond order for each carbon hydrogen is 1. Benzene carbon 6 hydrogen 6 D6H. The 6 pz orbitals on carbon atoms combine to give a set of 6 delocalized pi molecular orbitals. 3 bonding pi 1, pi 2, pi 3 and 3 antibonding pi star 1, pi star 2, pi star 3. The energy ordering follows the Huckel pattern: alpha plus 2 beta, alpha plus beta, alpha, alpha, alpha minus beta, alpha minus 2 beta. 6 pi electrons fill the 3 lowest molecular orbitals, giving a total pi bond order of 6 minus 0 divided by 2 equals 3. That is, a double bond spread equally over the ring aromatic stability. This delocalization explains benzene's equal carbon-carbon bond lengths approximately 139 picometers and its extraordinary chemical inertness compared to isolated double bonds. Explanation below are 4 typical examination-style tasks and a brief guide on how to answer them using MO concepts. I derive bond order and predict magnetic nature. Write the MO diagram for the given molecule, for example O2. Fill electrons according to the Aufbau principle Pauli exclusion and Hund's rule. Count bonding NB and antibonding NR electrons. Compute B, O equals NB minus and a divided by 2. Inspect the highest filled MOS. If any contain an unpaired electron state, the molecule is paramagnetic, otherwise diamagnetic. Roman 2. Explain anomalous bond lengths. Compare the calculated bond order with experimental bond lengths. An unusually short bond for a given period often indicates a higher BO than predicted by a simple Lewis structure, for example N triple bond N. Use MO ordering sigma pi mixing to rationalize why O2 has a bond length longer than expected for a double bond presence of 2 electrons in pi star. Antibonding MOS reduces BO to 2, lengthening the bond. Roman 3. Compare MO and VB predictions. Choose a molecule where the 2 theories differ, for example, O2. VB predicts a double bond with all electrons paired diamagnetic. MO correctly places 2 electrons in pi star antibonding orbitals, giving BO equals 2 and 2 unpaired electrons paramagnetic. Discuss how MO accounts for delocalization and magnetic data, whereas VB relies on localized electron pairs. Roman 4. Sketch MO diagram for a given molecule. Identify the valence atomic orbitals, note their symmetry, and order them sigma star pi star. Draw a ladder diagram, label each level with its symmetry and number of electrons. For heteronuclear species, indicate the unequal contribution larger coefficient on the more electronegative atom. Include the overlap energy gap comment if needed. This drawing demonstrates understanding of orbital mixing and electron allocation. When writing exam answers, use clear headings, show the step-by-step electron filling, include the bond order formula, and conclude with the physical property bond length magnetism stability that follows from the MO analysis.